Andrew.
Good evening, Enrique, and thank you very much for the introduction. And let me start this just by thanking the Mestrolab team for putting on this series of webinars and the Benchtop NMR session at ENC. It was really fantastic, and this has been a very exciting series of presentations. I'm going to present today on the topic of using Benchtop NMR to follow chemical reactions. One of the pleasures I get to do is to present the work of many other people. So I really must first thank the many customers who've contributed data and results for this presentation, and also the scientists and engineers inside Magritek who've done some of the work here as well. So thank you all. So a brief outline of the talk. I'll talk just briefly about Magritek and about benchtop NMR and MRI instruments. I'm going to spend a little bit of time talking about the Spinsolve Benchtop NMR Spectrometer that we manufacture and sell, and a little bit about the performance characteristics of that instrument, focusing particularly on those that are important for reaction monitoring. Talk a bit about reaction monitoring itself, but I want to spend the bulk of the talk and presentation today running through a series of different applications and examples which highlight some of the characteristics and features of monitoring reactions by NMR that just make it so exciting and interesting. So Magritek was founded over 10 years ago in 2004, and our focus has always been from the beginning developing mobile and benchtop NMR and MRI instruments. The original IP came out of research from Professor Bernhard Blumig's group in Aachen in Germany. Bernhard was an Ampere Prize winner and was one of the sort of original instigators of the concept of mobile NMR itself. Professor Paul Callaghan here in New Zealand was a Gunther Laukian Prize winner, and one of the many things he was famous for in NMR was developing NMR instruments that could be taken down to Antarctica to measure sea ice. And in that process worked out some of the, solved some of the problems around making NMR instruments robust and suitable to be taken into these kind of hostile environments. Today Magritek has companies, we have manufacturing and research facilities in Germany, here in New Zealand, and we also have an office in the USA and a network of distributors and agents around the world. So why would you focus on building small benchtop NMR instruments? And the reason is quite simple. For those of you who do have experience with high field NMR or traditional NMR instruments, which are based around superconducting magnets, the whole philosophy behind those systems, because they are so large and expensive and complicated to operate, is that you generate your samples wherever they are in the lab, and you take those samples to the spectrometer, which might be in the basement or might be in the building next door if you're lucky, or it could be a drive of 30 or 40 kilometers to get to the nearest instrument so you can measure your samples. And what benchtop NMR does, which is very similar to some of the same technology changes that have happened in other instrumentation, is it really opens up and democratizes this technology. So it makes it much smaller. As it becomes smaller, a lot of the cost is taken out, so it's more affordable. You can make it much easier to use and much more robust, so you can take it into a wider range of environments. And the concept completely reverses. You now take the spectrometer to the sample or to the reaction vessel where you want to make your NMR measurement. Now, Magritek doesn't only make benchtop NMR spectrometers. We also manufacture MRI instruments. In this column here, we've got the Terra Nova, which is an MRI education system. We also do benchtop imaging systems. In this slide here, I've actually plotted from the left to the right in an interesting way, looking at the very homogeneous fields on the left, which you need for spectroscopy, all the way through to very inhomogeneous fields on the right, where you get the fields of time domain NMR. And this is where you use parameters like T1 and T2 in diffusion. One of our instruments is the NMR mouse, a single-sided instrument, NMR instrument, and we have a rock core analyzer instrument, which is specifically for measuring core samples that come out of hydrocarbon reservoirs. So let's just, in this talk, I'm going to focus just on benchtop spectroscopy and just think a little bit about why that's so interesting and the kind of applications you've got. Obviously, the potential now to have an instrument that students can use is very compelling. You can put an instrument in your analytical lab alongside your other analytical instruments. If you're a synthetic chemist, that's very powerful. I'm going to talk, obviously, in this talk about reaction monitoring and also monitoring reactions in the fume hood, but also whenever you want to move NMR around, if you want to use it for QA/QC purposes, and ultimately to try and bring NMR as a process control method into chemical production, which is, you know, chemicals are produced all around the world in many, many different industries. So briefly, some of the features of the Spinsolve. So inside we use a cryogen-free permanent magnet. This is a Halbach geometry, which has some very specific advantages for benchtop instruments. We have a range of instruments which have the ability to access different nuclei, so not just proton but also fluorine, phosphorus, and if you're doing organic chemistry or organic reactions, carbon-13 is particularly interesting. Use regular 5mm NMR tubes, or you have the option to flow the sample through the bore of the magnet, which is obviously something we'll focus on a little bit in this presentation. There's no stray magnetic field outside the box. There's a built-in field lock to keep that magnetic field stable. And actually inside the apparatus there's no moving parts other than the fans. It's very easy to operate, robust, it's affordable, and it fits on a bench. If we do a brief cutaway, there's obviously a lot of hardware features in there, but just two I want to draw your attention to here. The first is that the bore moves all the way from the top to the bottom of the instrument. So if we want to flow a sample through the system, we can do it through there. And the second is, I just wanted to highlight in red here a number of the electronics and system features which are all designed to stabilize the temperature and stabilize the hardware. And the reason for this is permanent magnets that we use in benchtop instruments are all intrinsically very sensitive to temperature. I think for samarium cobalt, which is the material that we use, the temperature drift is around 400 ppm per degree Celsius. So you really have to stabilize both the environment that the magnet's in and the temperature of the magnet in order to have a stable magnetic field. And that stability is critically important, because having a stable magnetic field is ultimately going to dominate or determine how homogeneous a magnetic field you can generate. And the homogeneity of the magnetic field is ultimately what determines the performance of your NMR system. In traditional NMR, we use two measures to characterize how homogeneous or what resolution we can get out of our magnet. We use the half height at 50%, typically on a dilute sample of chloroform. So you can see here, here's the chloroform peak. It's just a single scan. And at 50% on this particular magnet, we've got a very nice line width of 0.15 Hertz, which is actually better or similar to a lot of high field magnets. And then the line shape, which is to do with how much of the signal from the NMR spectrum is sitting down in the baseline here. We measure that by looking at the width of the NMR signal at the height of the carbon satellites. And the carbon satellites being, I mean, the carbon-13 is 1.1%, so the carbon satellites are 0.55% down, which is here. And on this example here, we've got an 8 Hertz line shape, or line width of 0.55. This is a single scan and there's no sample spinning. The advantage of having this great line shape is all of that signal is pushed up into the line. So the narrower the line is down here, not only do you have better resolution, that's your ability to distinguish different lines, but you also have a much higher signal as well, which is why the line shape can really be a big factor in the sensitivity of your system, the sensitivity performance of your system. The other factor I mentioned was stability. In order to demonstrate the stability here, we've taken an ethyl crotonate sample and we've just acquired one scan every 30 minutes. This is 250 scans in this plot here. There's no shimming in between the scans, so in fact if you work that out, that's around 5 days of experiment. And if we just zoom in on this doublet of doublets here and stack all those lines one on top of each other, you can see remarkably 5 days of NMR scans one on top of each other with almost no change, no perceptible change whatsoever. And that stability is very important. In fact, it's particularly important when we think about reaction monitoring, because we want to monitor experiments over a period of time. We want to carry out an experiment, we want to measure and repeat a scan, maybe not every 30 minutes, but every minute or 2 minutes, and we might want to monitor a reaction for 8 hours or 10 hours. So that intrinsic stability is critically important. Also with stability becomes repeatability and consistency, again very useful characteristics of your measurement. But as I mentioned before, having more stability actually enables you to get a more homogeneous magnetic field, and that homogeneity leads to better line width and line shape, and that line shape leads to better sensitivity. All critical parameters when it comes to making successful NMR measurements. So let's now think about the application of reaction monitoring. So the idea here is we can follow a reaction using NMR. Typically we display the data in a waterfall plot like this. The Mestrolab MNOVA software does a very nice job of this, and you can see as this reaction is progressing we have some peaks appearing and some peaks disappearing, and we actually even have other peaks which as they're increasing in height they're also shifting on the chemical shift scale. What makes NMR so valuable in terms of reaction monitoring is a number of features intrinsic to the measurement. So NMR is very specific. It gives you completely definitive chemical information. And that information is not only sensitive to what molecule I've got or the molecular structure, but also the reaction kinetics. It's a bulk measurement. You're measuring the whole sample, not just the surface or a small point as you are with some other techniques. And it's non-destructive, so the sample can be pushed back into the reaction vessel. It's quantitative. NMR is intrinsically a quantitative method, so the NMR signal is linearly related to the concentration. It's not sensitive to matrix effect, and it doesn't require constant recalibration. And probably most surprising of all is you can use NMR in a flow environment. So as long as you follow a few simple rules, you can actually have a closed loop flowing system and measure using NMR on that flowing sample. The data is very easy to analyze and interpret. So the setup that we're going to talk through here, or that's used in most of these reactions, is something similar to what's in this picture, or there might be a slight variation of it, but typically we take the Spinsolve, it might be in a fume hood or in a chemistry lab, and we put it up on a stand, and you'll see, as I mentioned before, there's a bore that runs all the way through the magnet from top to bottom, and you can put a flow cell in here or run PTFE tubing. There's a number of different geometries and strategies that we use there. You might have your reaction vessel down here, and you can have a pump over here, and you can see, if you can look closely, there's actually some tubing from the reaction pumping through the spectrometer and back into the reaction vessel. Just to make it a little bit more, of an easier to follow graphic here, this is a slightly different diagram here where we've got a dewar in there and we're running PTFE tubing here, but you can see some typical kind of parameters that might be in a small closed loop real-time flow NMR setup. Very easy to set up, very convenient, and this is how most of these reactions that I'm going to walk through are done, like this or something similar. So let's get on to some examples. The very first one I want to talk about here is the hydrolysis of acetic anhydride. There's a number of important features of this reaction that I just wanted to call out immediately. The first is that this is a reaction done in water. This is pure protonated water, And that's something that most NMR spectroscopists would think, well, you know, surely you're using a deuterated solvent. In fact, you don't have to. You can use a protonated solvent. Here's the large water peak here. The acetic anhydride and the acetic acid peaks, which are the reaction, are these little small peaks off to the right here. If we look in the top right of the slide, again, zooming in around 2 ppm, you can see there's one peak that disappears away, and there's another small peak that increases on the right here. And you'll note that the concentrations here are less than 1% volume concentration for those reactants. So even though we've got a very large, you know, 99.5% of this volume is water, we can quite easily and accurately follow a reaction of acetic anhydride. You can see quite clearly here after 60 minutes we've got almost complete conversion. If we integrate those peaks, we can actually follow the production of the acetic acid here, the consumption of the acetic anhydride, and you can even run a mass balance and show that you're capturing all of the protons in that experiment. Even more interesting, you can run the reaction at different temperatures. And if you repeat that same experiment, but here at 4 different temperatures from 5 to 43 degrees Celsius, you can see, as is well known, the reaction will occur at different reaction rates. We can take those reaction rates and plot them on a Arrhenius plot. So this is the reciprocal of the temperature against the reaction rate, and you should get a straight line, which we do, and from that we can get the activation energy, which agrees very nicely with other measures of it. If you want to see a little bit more about this particular application, we've got an application note on our website, and the URL is down there. The second experiment I wanted to show here is again a reaction in water. This is one where it's not as clean and nice as the acetic anhydride one. This is monitoring a fermentation, and this is a fermentation that one of our scientists here at Magritek likes to do, which is making apple cider from apple juice. You can see in this bottle here, it's a yeasty mixture which is cloudy. It's a bit, it's got lots of bubbles in it. It's not particularly a nice chemical reaction that's going on, and something that you might feel a little bit afraid to pump through an NMR spectrometer, quite unsure what you're going to get. Well, we carried out that reaction. So there was a little reactor here with the yeast and the apple juice. That was left running over the weekend, and every few minutes we acquired an NMR spectrum. And here we're just going to zoom in on the 1 ppm region where we expect to see the methyl peak of the ethanol. And sure enough, as the hours progress, you can see this methyl peak appearing. And we can follow it on this graph here. You can see the methyl peak integral increases with time. I want to call your attention to this line here at 10 hours. The spectrum here at 10 hours, it looks like everything's disappeared. And if we look at the integral down here, it's sitting down at 0. And actually, it doesn't take much to realize what's happened there is a bubble has flown up through the tube, and at that particular point in time, it went to measure a bubble. There was no sample there, and so recorded very little. But it turns out this really doesn't matter. You can take your NMR data there, you can remove the points which sit around 0, and you can run this reaction out for, I think in this case, about 250 hours, calculate the ethanol percentage from that integral of the methyl peak, and look, you can see the ethanol increasing very nicely. You can see very clearly where the reaction endpoint is here. You can take the slope of this line and actually derive a conversion rate from that, and even see at what point did we have the maximum conversion rate, and again, what point did it return to 0. Now, rather than point you to this application note, I'd like to draw your attention to this very recent publication in Biotechnology, Bioengineering by Professor Blumig's group, and this is a really fascinating paper that pulls a lot more detail than what I've shown you here about that reaction, and goes into some of the really some of the fine points of what's achievable. It's a very good paper to look at. The next example I want to show is, now instead of looking at just proton NMR, what about looking at other nuclei? And in many industrial chemical reactions and pharmaceutical reactions, there's also fluorine as well as proton. Fluorine is a very nice NMR active nucleus. It has a spin half, it has a good gyromagnetic ratio. One of the nice features of this benchtop NMR system, the Spinsolve, is you can do proton and fluorine acquisition sequentially. You can switch from one nucleus to the other in no time at all. And so they're following a reaction here, which has a sort of a fluorinated methyl on the end here, going through this reaction, and over time they are switching from, they're doing one proton, then a fluorine, then back to a proton, then back to a fluorine. What's really useful to notice here is in the proton spectrum, the product that is being created is overlapping, the peaks of that product are overlapping a little bit with some of the starting material. Whereas in the fluorine spectrum, with the much wider chemical shift dispersion that you get on fluorine, those two peaks are completely separated and can be integrated and followed without overlapping. One of the interesting things about the group that did this work, this is Michael Myhrvold's group at the BAM Federal Institute for Materials Research and Testing in Berlin. One of the interesting things about their lab is, unlike most other labs, they actually have a high field system that they can do reaction monitoring with as well. And in this experiment here, they ran their reaction simultaneously through the Spinsolve benchtop NMR and then through a 500 megahertz high field system, which was especially set up to do reaction monitoring. And you can see here, obviously with the high field system, there's much better signal to noise, there's a lot less fluctuation on it, but in terms of the data that's being collected and the results, you can see there's very, very good agreement between the high field data and the benchtop NMR data. The obvious advantage of the benchtop system is you can then take it out to a plant or a site and actually monitor it on the reaction in a real environment. They just alerted me the other day there's a publication of some of this data in JMagRes, and I've got the reference for you down there if you want to go and have a look, also in magnetic resonance in chemistry. So if you want to look at that in more detail, there's the reference for you. Another customer of ours is Lee Cronin's group in the University of Glasgow, and they had an excellent publication recently in Chemical Science. Part of the paper was following an imine synthesis, and in this reaction the products are coming together and then they're holding them for different residence time in the reaction and looking at the yield of the reaction. So depending on the residence time here, the yield increases as a function of that. And in fact, this fits very nicely with second order kinetics, and again, compared to optical methods like ATR infrared, there was no additional calibration or correction needed in order to get the reaction kinetics directly from the experiment. A quite remarkable experiment that they then did as a follow-on to this was setting up this apparatus here, where they used 3 different starting materials, including the catalyst. We've labeled them here, or they've labeled them X1, X2, X3. They've got the reactor with a variable residence time, and they're using the benchtop NMR to actually monitor the yield of the reaction, as I showed in the previous slide. But now they feed that yield back into an iterative program that then uses an algorithm to step back and repeat the reaction and try different values of the starting concentration and residence time to try and find the parameters that give the maximum yield. So this is a completely independent, they use a Nelda-Mead algorithm, so it's a completely independent self-optimization of a reaction. So a typical spectrum is here, showing one of the starting products and showing the product that's produced. And you can see here, as they step through the iterations, the yield J increases, sometimes it goes down, but ultimately the algorithm is able to find a set of parameters with an optimal reaction yield. So the reference is down the bottom there if you want to look at that in more detail. It's a really quite remarkable experiment. When we're looking at other nuclei, obviously with NMR, a nuclei that's very interesting is phosphorus-31. It's a great nucleus to measure. There's a very, very large chemical shift range, and it's often found in a lot of organic compounds, especially DNA and membranes. And of course, from an NMR point of view, it's quite nice because there's no solvent or background signal. And here's a nucleoside phosphoramidite that's been produced in a reaction. And just using phosphorus NMR as a QA/QC tool to look at the impurities, which are these little bumps down the bottom here that have been expanded on the graph on the right. One of our scientists in-house did a very nice little reaction following phosphorus, which is this triphenyl phosphine oxidation reaction. She did it in the NMR tube here, so you can see here's the elemental sulfur at the bottom. Here's the solution in the NMR tube. Now you can follow this reaction using proton NMR, but the spectrum is very crowded and it's quite difficult to follow. The phosphorus NMR spectrum is simply remarkable. So if you want to follow a simpler reaction than this, I would struggle to find it, because here you have one peak on the right, which slowly decreases. There's one peak on the left which increases with time, so this is successive time as we're going up the axis there, and you can integrate that and see very nicely the consumption of your reactant and here's the product being formed here. And there's even a small tip at the end here, which is where some of the product started to precipitate out of the solution. So with the wide chemical shift, with the large chemical shift, we're starting to observe spectra that are not that dissimilar to the spectra you might observe on a high field instrument. Now, moving sideways quite a lot, one of the new areas of development in NMR, and actually of particular interest to MRI, is the reactions which lead to hyperpolarization of target molecules. This is some work here done again in the Aachen group by in Bernard Blumig's group, and here they're taking a pyridine with an immobilized catalyst. They're running the pyridine through the catalyst with parahydrogen, and as you can see, here's the thermally polarized signal, and suddenly you get this huge increase in polarization as a result of transfer of spin order from the parahydrogen onto the pyridine molecule. This has a lot of interest for MRI and other applications, and is an area of research at the moment that's very exciting. Now, increasing polarization actually opens up a whole new area of possibilities to use NMR in reaction monitoring. The data I'm going to show here comes from Franz Schilling group in the Technical University of Munich, and this is using a hyperpolarizer to polarize a carbon-13 molecule. In this example, first example here, this is the carbon-13 NMR spectra of urea, and because we can get such high polarization, we can use very small tip angles, or they use very small tip angle RF pulses here to very quickly measure T1 with a high SNR. Now, what they've done with this is taken it a whole step further to actually monitor metabolic reactions in real time. And this data here is pancreatic cancer cells in a culture medium. They've added hyperpolarized pyruvic acid, which is this peak here, and they've followed the reaction. So this is just time increasing here, a few seconds there. And you can see here this peak, which is lactic acid growing, and then as the hyperpolarization runs out, it dies away. So you're actually following a metabolic reaction here using carbon-13 NMR real-time reaction monitoring, which is really quite remarkable when you think about how difficult it is to do carbon-13 NMR in any ordinary situation with normal thermal polarization. So just showing the same data again, here's the pyruvic acid, here's the reaction that's going on, here's the lactate being formed, and again we can see the production of this lactic acid here as some of the pyruvic acids being consumed. Another type of reaction that occurs in chemistry is not changing the molecules, so we're adding atoms to molecules to make new ones. It's when a molecule changes its shape without changing its structure. And this experiment here is looking at glucose anomers. Glucose has an alpha and a beta form, which are isomers of each other. In normal thermal equilibrium, it has 64% beta and 36% of the alpha form. They're in equilibrium with each other here. This is a 1D spectrum that one of our scientists acquired. In fact, to move this, this residual HDO peak, they actually heated the sample to 90 degrees C and were able to measure it, and you can see with the integrals there you've got the equilibration that you expect. There's an application note on our website, you can look in more detail there. This is called a muto-rotation reaction. So in this experiment, they started off with pure alpha glucose, and they followed it over a number of hours, over 2 hours, and you can see here the alpha glucose peaks disappear and the beta glucose peaks here, and again you can very easily follow it and get a reaction rate very simply and very quickly. This can actually be analyzed even with the HDO peak there. You can just take the integral of the whole one and subtract off the alpha glucose and monitor this one as well. So it works very nicely. I want to spend the last few slides of this talk just to have a few slides about mixtures, because reactions are inherently mixtures of different chemicals. Something that's often done at the end of a reaction in a chemistry lab is to take the mixture and pass it through a column chromatography in order to try and separate the mixture into its different components. So you've got the column chromatography here, and you've got these series of different tubes at the bottom that the different fractions will run out into. And often TLC is used, thin layer chromatography is used to try and see, you know, what has made it into which tube. Now, we set up a sort of an example here where we've taken 4 molecules, we've mixed them together in different proportions, and the spectrum you can see down the bottom here, this green spectrum, is our mixture of 4 different molecules. And on the right here, we've got an TLC of one of those fractions that came off, and you can see there isn't very good separation between the 2 components that are in that particular one, and of course we don't know which one is which. We don't know which one is here and which one is there. So we ran it through the column chromatography, and we took the 30 odd samples that came off, the fractions that came off it, and here they are plotted from 1 all the way up to the top here. So this is not so much following a reaction, but following the different components, trying to separate out the different components of a reaction or of a mixture. We've cut out from the center here the large dichloromethane peak to make it a little bit easier to see, but immediately you can see straight away where the 4 different components of this mixture have come through the column chromatography. And over here you can see quite easily that on this particular one we had 2 of them came through, and because we know what the NMR spectra are, because we have that specificity that we have with NMR, we know immediately which molecules they were. Just the last couple of slides, I want to talk about I guess the traditional way that people try and separate molecules in mixtures is you use chromatography. And in chromatography you have the different the molecules which have different sizes, and they pass through a column at different speeds depending on the type of molecule, and how big it is determines how fast it moves through the column. In NMR we have a very interesting method that was developed in the 1970s by Seskel and Tanner, and that's called the pulse gradient spin echo experiment. And in this experiment we use a pair of gradient pulses, and as we increase the strength of those gradient pulses, and that's increasing here from 1 up to 16, we find the NMR signal is attenuated, but how much it's attenuated depends on how fast the molecule is moving. Now all molecules in a liquid mixture are moving, it's called Brownian motion or self-diffusion, and typically the larger the molecule, the slower it moves. You can see quite clearly here there's a peak sitting just below 5 ppm, which is the HDO peak, and this peak decays quite quickly because the HDO is a pretty small molecule. This solution, by the way, is 8 milligrams of caffeine in half a mil of D2O. The other larger peaks here at 3 and 4 ppm and up at 8 ppm, they're the caffeine molecule, which is larger, and you can see they decay a bit slower. And this experiment is called the DOSY experiment, or diffusion ordered spectroscopy, and there's some nice software around which lets you process that data so that you have chemical shift. You have a 2D plot with chemical shift along one axis and the self-diffusion coefficient along the other axis. And you can see quite clearly here we've got one peak here, which is the H2O, and here we've got the 4 peaks of caffeine completely separated from the solvent, the HDO peak here. So if you think about it, DOSY it's almost like a form of in situ chromatography, a way of separating out the different components of a mixture without actually separating them. This, of course, is going to be incredibly useful for reaction monitoring, where we're almost always working with mixtures, and the ability to separate them by self-diffusion coefficient could be very useful. Unlike chromatography, of course, it's non-destructive and it could be used in line. And again, because we use, we often have solvents that we want to either suppress the signal from or separate from, again, this method could be very, very useful. So I want to just summarize some of the things I've covered here. I guess central to this talk is the idea that chemical reactions are very important things. They're in many industries and many processes, pharmaceutical industries, chemicals, food, fuels, polymers. They're all industries that use chemical reactions at the heart to make the products that they develop. Monitoring chemical reactions enables us to measure them, control them, and optimize them, which in turn allows us to improve the yield of those reactions, the quality of the materials we produce, and also the efficiency, how long it takes that reaction to run in order to produce the desired material at the end. NMR has always been an ideal method for reaction monitoring. In fact, today people still gather their samples and drive them off to an NMR lab to see if their reaction worked. However, you're always stuck with the paradigm of having to take your sample to the spectrometer. So the Spinsolve Benchtop NMR system allows you to now take the spectrometer to the environment where your reaction's going on, whether that's your chemistry lab or in a pilot plant, and put that instrument right next to the reactor. The Spinsolve Benchtop NMR, of course, you don't just have to use NMR, you can use it alongside other optical chromatography methods. And one of the things that seems to be coming through quite strongly is that the information you get from NMR is quite orthogonal to the information you get from these other methods. So it can be complementary and expand the information and knowledge that you've got about that reaction you're trying to follow. And finally, just to emphasize again that the sensitivity, resolution, stability, the many different methods that we have in NMR, the multi-dimensional and multi-nuclear methods, are all important tools and important features to pay attention to if you want to have successful benchtop NMR reaction monitoring. And with that, I'd like to thank you very much for your attention, and I'm very happy to answer any questions that might have been generated during the discussion. Right, I'll have a look at the list here. How many scans were performed on the phosphorus oxidation reaction? I'm not entirely sure, to be honest, but I could certainly get the answer to that and email it through to you. I'd have to talk to the scientist who did that. I don't think it was a huge number, but I'll go and get that information. How long does it take to change from proton to fluorine if you follow the reaction by both? Actually, the answer is it's instantaneous. There's no change in the electronics. You just pulse at one frequency and then you pulse at the other frequency. For the time difference between that particular experiment that was done by the other group, we'd have to look at the publication, but typically you might do a 5-second acquisition on proton, and then you do a 2 or 3 second acquisition on fluorine, and you could switch backwards and forwards between the nuclei on a 10 or 15 second repetition time if you wanted to. It's really quite quick. Another question here, can you follow the reactions at 43 degrees C directly, or do you need to cool down the sample before it goes into the spectrometer? This is actually a very good question, and it's actually something we're working on a lot at the moment. Generally at the moment the reactions are cooled down to the temperature of the magnet, or close to the temperature. So I think if you cool them down to around 30 degrees Celsius, then they can pass through the spectrometer without any issues. There is a time period that you can pass hotter samples through, so there is a certain amount of time where you can follow a hotter reaction, but if you allow too hot a liquid to pass through for too long, then it will eventually, that heat will eventually get through to the magnet. I could actually find out directly what happened with that particular experiment. Any other questions coming through? Another question down the bottom here, can you confirm that the Spinsolve phosphorus apparatus offers the possibility to perform proton, phosphorus 31 and fluorine 19? Yes, I can. That's exactly the 3 nuclei that that particular instrument can do. So it's a dual channel system. It has phosphorus and it has proton. It's very important to have dual channel because you need to do proton decoupling for most phosphorus 31 experiments, and then that proton channel can also be used to measure fluorine 19. They're very close to each other in frequency, so the proton channel can switch between proton and fluorine, and then the second channel is used for phosphorus. Actually, incidentally, one of our scientists has some very nice data doing fluorine phosphorus 2D NMR experiments, so you can use on the second channel the fluorine and on that main channel phosphorus 31. Another question down the bottom, can you follow a reaction with proton, fluorine and phosphorus at the same time? Yes, you can, as long as you acquire one after the other. You can't acquire them simultaneously at exactly the same time, but you could do a proton scan, a fluorine scan, and then a phosphorus scan, and then come back and do a proton, a fluorine, and another phosphorus, and keep following that. In the latest version of our software, the 1.4 version, there's some very, very powerful scripting capability that's been introduced, which really allows you to set up whatever scheme you want to do for measuring a reaction and for doing a series of experiments one after the other. So, for instance, you could do a 1D proton, you might acquire a COSY, you could do phosphorus, and maybe the phosphorus has a number of scans on it, then a fluorine, and then repeat again and go back to proton again. So it's really very flexible and gives you a huge amount of control about how, what kind of acquisition strategy you want to use for following your reaction. Is it possible to do phosphorus coupled to proton? Well, we have proton and phosphorus. Generally with phosphorus we do, with the 1D experiments you want to do decoupled experiments on the phosphorus. I think we have, I'd have to go and check, I think we have some proton phosphorus 2D experiments. I can certainly get one of our scientists to come back and confirm that. I'm probably going to have to finish up soon because I think I'm gone well over the time. Yeah, I think that's probably going to have to do. So I'd like to thank you all again for turning up. I know the timing here was not good for the United States, but hopefully some people get to watch the video later on. I'd like to thank you for your attention and hope you have a great day. Thank you very much.